So the next rational function that we're going to graph is f of x equals x squared minus 4x over x squared minus 16. Okay. And we got to find all the information requested before we graph it. And so the first thing we got to do is find the domain and interval notation. And we've done this many times. Okay. So to find the domain, right, you take the denominator and you set it not equal to 0, and then you solve for x, right? So when we factor the left-hand side, we have x minus 4 times x plus 4 can equal 0. So the factor x minus 4 can equal 0, and the factor x plus 4 can equal 0. So we get x can't equal 4, and x can equal minus 4. Okay. So in interval notation, right, the domain in interval notation is minus infinity to minus 4 union minus 4 to 4 union 4 to infinity. The range, right, we got to save for last until after we graph the rational function. Okay. The next item is the coordinates of the x-intercepts and the coordinates of the y-intercept. Okay. So before we do that, we have to eliminate any factors, common factors in the numerator and denominator. And so you can see that the numerator factors into x times x minus 4, and the denominator, we already know, factors into x plus 4 times x minus 4. Okay. So you can see x minus 4 is a common factor in the numerator and denominator. And from section 1.5 in the semester, when we were reducing rational expressions like this, right, we said we could cancel out the common factor x minus 4 in the numerator and denominator as long as x doesn't equal 4. Okay. And so this simplifies to x over x plus 4 as long as x doesn't equal 4. Okay. If x equals 4, we got 0 over 0, which is undefined. Okay. And so we call this reduced form. Okay. And now to find the x-intercept or intercepts in the graph of this rational function, we set the numerator of the reduced form equal to 0. Okay. And so when we set the numerator equal to 0, we just have x equals 0. And so the location of the x-intercept, right, and it's asking for the coordinates. Right, the coordinates of the x-intercept. Well, the coordinates is 0, 0. Okay. So the x-intercept is located at the origin. Okay. And likewise, right, we're going to find that the y-intercept is at the origin. Okay. To find the y-intercept, you set x equal to 0, and it doesn't matter whether you use the original rational function or the reduced form. When you evaluate the function x equals 0, you have 0 over 0 plus 4, which is equal to 0. So the y-intercept is also at the origin. Okay. All right. Now, to find the equation of the vertical asymptote or asymptotes, okay. Well, the common factor of x minus 4 in the numerator and denominator creates a hole in the graph, if you remember from section 1.5. Okay. So to find the vertical asymptotes, okay, you don't use the original denominator, the original rational function. You use the denominator of the reduced form. So find the vertical asymptotes for this rational function. We take the denominator in reduced form, we set it equal to 0, and then we solve for x. So the equation of the vertical asymptote for this rational function is x equals minus 4. So remember, vertical asymptotes are vertical lines, okay? So the vertical line x equals minus 4 is a vertical asymptote, okay, in the graph of this rational function. Okay. Now, to find the equation of the horizontal asymptote, we haven't talked about this case here, okay? But you have to consider the degree of the numerator and the degree of the denominator in the rational function. So in the original form of the rational function, the degree of the numerator is 2. The degree of the denominator is also 2. So they're of equal degree. And if you look at reduced form, right, the degree of the numerator is 1. The degree of the denominator is 1. Okay? So whether you look at the original rational function or the reduced form, you can see that the numerator and denominator are of equal degree. And so then the question is, what is the equation of the horizontal asymptote when the numerator and denominator are of equal degree? Okay. So if you flip over back to page 3 in your lecture handout, in the middle rectangle, it talks about what the equation of the horizontal asymptote is, okay, in case number 2 down here, when the numerator and denominator are of equal degree. If the degree of the numerator equals the degree of the denominator, okay, then the equation for the horizontal asymptote is the horizontal line y equals this fraction. The numerator in the fraction is the leading coefficient of the numerator, and the denominator in this fraction is the leading coefficient of the denominator. So if you look, doesn't matter whether you look at the original rational function or the reduced form, okay? The leading coefficient of the numerator is 1, right? The leading term is x squared, and the leading coefficient is 1. And the denominator, the leading term is x squared, and the leading coefficient is 1. In reduced form, right, the leading coefficient is the invisible 1 in front of the x in the numerator, and the leading coefficient in the denominator is the invisible 1 in front of the x. So the equation for the horizontal asymptote is the leading coefficient in the numerator divided by the leading coefficient in the denominator, which is 1 over 1. So the horizontal asymptote for this rational function is the horizontal line y equals 1. Okay. So when it's equal degree in the numerator and denominator, you just take the ratio of the leading coefficients to get the equation of the horizontal asymptote. Okay. All right, next it asks the equation of the slanted asymptote. Okay. So up until now, we've been dealing with vertical asymptotes and horizontal asymptotes, right? Vertical asymptotes are vertical lines, horizontal asymptotes are horizontal lines. A slanted asymptote is a slanted line, right? It has slope, right? Positive slope or negative slope. So to find the equation of the slanted asymptote, if there is one, is given in the third rectangle on page 3. Okay. And this special case says if the degree of the numerator is exactly 1 more than the degree of the denominator, then the graph of the function has a slanted asymptote. Okay? So the degree of the numerator has to be exactly 1 more than the degree of the denominator. Well, the degree of the numerator is not 1 more than the degree of the denominator. They're of equal degree. So the graph of this rational function does not have a slanted asymptote. Okay. So in the blank on page 5, where it says equation of the slanted asymptote, you just write none, okay? Because they're of equal degree. Okay. All right. Lastly, it asks you for the coordinates of any hole in the graph. Okay. Well, we know there's a hole in the graph because of this common factor x minus 4 in the numerator and denominator. We know there's a hole in the graph at x equals 4. Okay. Common factor x minus 4 in the numerator and denominator, right? You set that common factor equal to 0, and when you solve for x, you get x equals 4. That's the x coordinate. Okay? That's the x coordinate for the hole, where the hole in the graph is located at. Now, to find the y coordinate, you evaluate the function at, you evaluate the reduced form at x equals 4. You can't put 4 in for x in the original rational function because you're going to end up with 0 divided by 0, which is undefined. So to get the y coordinate, you use the reduced form. So you set y equal to, and we put 4 in for x. We have 4 over 4 plus 4, which simplifies to 1/2. So y equals 1/2 is the y coordinate, right? Where the hole in the graph is located at. So the hole, coordinates for the hole in the graph is the point 4, 1/2. Okay. So that's what you can fill in the blank down here. Coordinates of any hole is the point is located at 4, 1/2. Okay. And now we have all the information we need, okay, to graph this rational function. So I have provided you with a grid. Here's coordinate plane, okay, and there is a vertical the vertical line x equals -4 is a vertical asymptote. So we draw a vertical line that crosses the x-axis at x equals -4. Okay. -1, -2, -3, -4. Okay. And then y equals 1 is a horizontal asymptote. So we draw a horizontal line that crosses the y-axis at y equals 1. So the vertical asymptote crosses the x-axis at -4, and the horizontal asymptote crosses the vertical axis at y equals 1. Okay. Now this is the origin, and both the x and the y intercept is at the origin. So we can put a circle there. Okay. And lastly, but the hole in the graph is at the point 4, comma 1/2. So to plot that point, you go to x equals 4, and then up 1/2 unit, and y equals 1/2 is between the origin and y equals 1, and you graph the open circle at the point 4, 1/2. And now, right, we can graph the rational function. Okay, so now we got to determine whether, we know that on the far right end, the graph is going to flatten out either above or below the horizontal asymptote, and it's going to flatten out either above or below the horizontal asymptote on the left end, right? Now here is what the deductive reasoning, the graph is going to go through this point and connect to this open circle, right? So it's going to go out here to the right below the horizontal asymptote, and I'm suspecting it's going to go down to the right of the vertical asymptote. Okay? But we can, test this. So to determine whether the graph goes up or down on the right side of the vertical asymptote, we plug in -3 into f of x and see if the value of the function is positive or negative. Well, and it doesn't matter whether you use the original rational function or the reduced form, right? Because you can't use the reduced form when x equals 4. You can use it for any other value of x. So f of -3 is equal to -3 over -3 plus 4, which is equal to -3, negative. So that means the graph goes down on the right side of the vertical asymptote. Okay? And it also means that the graph passes through the point -3, -3. Okay. So here's -3 on the x-axis, and you find -3 on the y-axis. So here's the point -3, -3. And so to the right of the vertical asymptote, the graph comes up, passes through that point, goes through the origin, and then it connects to the hole in the graph. It doesn't go through the hole in the graph, it connects to it. And then to the right of the hole in the graph, it continues to rise, getting closer and closer to the horizontal line y equals 1, but it doesn't cross it or touch it. And then you can put an arrow down here to indicate that the graph goes down further. Okay. It's not perfectly drawn, but it's pretty well drawn. Okay. And so that is what the graph looks like to the right of the vertical asymptote. And now on the left side, we got to determine whether the graph goes, left side of the vertical asymptote, we got to determine whether the graph goes up or the graph goes down. Okay. And so we can use x equals -5 as a test point to see whether it goes up or down. And again, when you evaluate the function at x equals -5, it doesn't matter whether you use the original form of the rational function or the reduced form. Okay? Both will give you the same answer. Okay? And so when I use the reduced form, and -5 over -5 plus 4, which simplifies to +5. So, since the value of the function is positive, right, we know the graph goes up on the left side of the vertical asymptote. We also know, right, -5 is the x-coordinate, 5 is the y-coordinate. We also know that the graph passes through the point -5, 5. Okay? So here's 1, 2, 3, 4, 5 on the y-axis. And so I'm going to extend my vertical asymptote. And so the graph goes up, right, on the left side. And then on the left side of the vertical asymptote, And then going out to the left, it's gotta come down and flatten out. Going to the left, right above the horizontal asymptote. Okay. And so that is a rough image, right? A rough sketch of this rational function. Okay. Any questions on that? Okay. So now the last thing we have to do is find the range of this rational function, right? In interval notation. And so this could be exam 1 question, right? Exam 1, you were given a graph of a function, and you had to determine the range from the graph, right? So we got like 2 parts of the graph here, right? So let's start with this part over here. On the right side of the vertical asymptote, the graph goes down forever, so there's no minimum y-coordinate, right? Remember, the range is the y-coordinates, so there's no minimum y-coordinate. And as we move along this part of the graph, right, the y-coordinates increase until we get to the hole in the circle, and that hole in the circle is located at 4 1/2 in the coordinate plane, where 1/2 is the y-coordinate. So for this part of the graph, all the y-coordinates go from -infinity up to 1/2, not including 1/2. So for the first part, the y-coordinates are all less than 1/2. -infinity to 1/2. To the right of the hole in the circle, right, the y-coordinates are greater than 1/2, but the further out you go to the right in the graph of a rational function, the closer the graph gets to the horizontal line y equals 1, but it never touches it. So all the y-coordinates are greater than 1, but less than, or all the y-coordinates are greater than 1/2, but less than +1. So for this part of the graph to the right of the hole in the graph, the y-coordinates are greater than 1/2 and less than 1. Okay. They go from 1/2 to 1, not including 1/2, not including 1. Okay. Now for this part of the graph, to the left of the vertical asymptote, right, on the immediate left of the vertical asymptote, the graph goes up forever, and there's no maximum y-coordinate. But as we go out to the left, okay, the y-coordinates decrease, but because the graph never crosses or touches the horizontal line y equals 1, the y-coordinates are all greater than 1. So for this part of the graph, the y-coordinates are greater than 1, but they increase without bound. And so for that part of the graph, the range is from 1 to infinity. Okay. So the range is all real numbers except for 1/2 and 1. And 1/2 isn't included because of the hole in the circle. And 1 isn't included because of the horizontal asymptote. Okay. Any questions on that, ladies and gentlemen? Okay. So if you flip over your page to the next page,